Hi, it's me, your teacher. I am just here to go over some of the stuff that we did at the end of last term. So looking at the size of K and the position of equilibrium. So whether products or reactants are favored in certain environments, and looking at Le Chatelier's principle. Let me just check myself. Yes, no, I am doing all of those things today. So if K is greater than 1, so the value of K is more than 1, we say that our products are favored. So favored just means that more products are being made than reactants, or that the concentrations of our products are greater than those of our reactants. Either of those is fine. If K is less than 1, so conversely K is smaller than 1, that means that our reactants are favored. So it is kind of important. I didn't really get to this at the end of last term because obviously we all had to go into hiding, but that is why K is a useful number. It's not just a number to talk about the ratio, it actually gives us information. So if it is bigger than 1, it tells us that our equilibrium lies more towards the products, so more products are being made than reactants. And if it's less than 1, that means that the equilibrium lies more towards the reactants. They are favored, and so more reactants are being made than products, or that the concentration of the reactants is greater than that of the products. Now, the reason for that is if you think about this like a fraction, so K is equal to products over reactants, K is equal to, or pork, products over reactants equals K. If we think about this like a fraction, when the top of your fraction, like the concentration of our products, increases, the value of the fraction also increases. So if we pretend that we start with 1 over 1, and if I increase the value of my top half, I increase the value of my products to 2, the overall value of my fraction increases. It went from 1 to 2. So as it gets higher, that means that the thing on the top, your numerator, is getting bigger. So in this case, for our K expressions, that means that my products are increasing or are bigger. Conversely, if the bottom of my fraction increases, the value of my fraction decreases. So if my reactants increase, that means that my K value is going to decrease. So if reactants are favored, the concentration of reactants is greater than that of the products, that means I'm going to have a smaller K. It's going to be less than 1. So that's why these statements are true. That's not what I wanted to do at all. That's why these statements are true if we think about it this way. So think about it like a fraction. Also, the magnitude of K can also give us useful information. So if K is greater than 10 to the power of 20, so that's a 1 with 20 zeros behind it, that means that the reaction effectively goes to completion. So that means that I have pretty much no reactants left, because my concentration of my products is so high. We wouldn't consider something with a K over 10 to the power of 20 to be in that dynamic equilibrium that we were talking about. It's more like a static equilibrium, like a brick, where it's not really probable anymore. We can't manipulate that reaction as an equilibrium reaction anymore. If K is less than 10 to the power of negative 20, so that's a 1 with 20 zeros in front of it and a decimal point, very, very small number, the reaction won't start. So remember that a very small number means that we've got more reactants than products. We basically have all the reactants and no products. So the reaction won't start, or hasn't started, because we have no products and we have such a massive amount of reactants. Okay, so the important thing to remember here is that our K value is only at equilibrium. So this is the ratio of products to reactants at equilibrium. the system, the reaction, will always want to get back to that ratio. They want K to remain the same, and K does remain the same, which is also an important distinction. So K only exists when the reaction is at equilibrium. At all other points, we call the ratio of products to reactants Q, or the reactant quotient. So basically at all other points apart from at equilibrium, the ratio of products to reactants is Q, or pourquoi, which we'll come to later, so don't stress too much about it now. But at equilibrium only is when they reach that equilibrium constant. And the whole point of an equilibrium reaction's being is to be at that ratio to meet K, to be at K, or when Q is equal to K. However, what we can do with an equilibrium reaction, because they desperately want to be back at K, is we can prod it. And we can force it to go in a direction it doesn't want to. We can force it to go back to Q and out of equilibrium. And that is Le Chatelier's principle. There are 3 different parts to Le Chatelier's principle, but the main tenet is that whatever you do to it, the system will react to remove that change you did. It doesn't want what you've done. You're being very rude. You're intruding on its private isolation lockdown time and ruining everything and stopping it from being in equilibrium, and it's going to try its best to reduce the effects of the change you caused. So there's 3 different ways that you can annoy your system. The first one is changing the concentration of something, either increasing or decreasing the concentration of a reactant or a product. The second one is pressure, so increasing or decreasing the size of the vessel that your system is in, which is functionally identical to concentration, but we'll talk a bit about it. And changing the temperature, which is the kind of the trickiest one. You'll be thankful to know after we go through this that really the only one you have to think about in this particular topic is concentration, because we're thinking about water. So, concentration, Le Chatelier's principle. So let's say that I am going to add more nitrogen. I'm going to add some more N2 to my system. So what have I changed? I've increased the concentration of N2, which means that my value of K, because I've added some reactants, is going to go down, or my Q is going to go down. I'm no longer at equilibrium because I've added this extra reactant. So the system is going to try and reduce the effects of change by using up that extra N2. The only way that it can do that is by making more product. So I've added some extra reactant, it's sitting there, the system doesn't want this extra concentration of N2 because it is messing up its perfect ratio at equilibrium. So in order to fix that, it has to make that N2 go away, and the only way it can make that N2 go away is by reacting it with H2 to make NH3. So it's going to use up that extra N2, and so therefore it is going to shift to favour the forward reaction. Or you can say that it is favouring products. So that means we're going to be going in this direction in order to use up that N2. If I instead took away some of that N2, so maybe I added something that reacted with the N2 so that it is removed. Again, the system is not pleased with this. It's not pleased with the fact that you just removed something that it worked so hard to have there to keep its system at equilibrium. So it is going to react by trying to make more. So I decreased the concentration of N2. And the system is going to reduce that change by making more N2. And it's going to do that by favouring the backward reaction. So turning NH3 into N2, or favouring reactants. Same idea happens if I added some NH3. The system would work to reduce that NH3 because they've added some. It doesn't want that extra. It's going to remove it, and it's going to do that by going in the backwards direction and using up some of that NH3 to make N2 and H2. Now, pressure. Pressure is kind of like, actually very similar to concentration, but you're thinking kind of more in 3D. So if you have your system in a closed container, so pretend this is a jar, and you have all of your molecules of gas bouncing around in there, they have come to a nice equilibrium where the number of moles of gas is the right fit for its environment. So remembering that gaseous molecules can expand to fit their space. So they've expanded to fit their space. It's a good space. We've got the right number of molecules bouncing around here. If I take the lid off of this system and they're allowed to spill out, suddenly their space has got a lot bigger. So they have a very few molecules in a very large space. So effectively their spatial concentration has massively decreased. So what it's going to want to do is it's going to want to make up for that. So I have increased the volume, or I have decreased the pressure, because they're not squished together, as much anymore. And in order to fix that, what it needs to do is make more molecules of gas. So it doesn't really care about what molecules it makes, it just wants to make more. So if we look here, on our left-hand side, we have got 4 molecules of gas, 1 from the N2 and 3 from the H2. And on the right-hand side, we have 2 molecules of gas coming from our NH3. So because I've increased this volume, I've given them all this space, and they want to fill that up with gaseous molecules, my system is going to shift in the backwards direction. Make more moles of gas to fill up space. So it's going to go from 2 moles to 4 moles, which means it's going to favour the backwards reaction. Conversely, if I took the same system and I stuffed it back into a much smaller jar and put the lid on, they're all very squished in there. There's far too many molecules in this space for the system to be happy. So what have I changed? I have decreased the volume, or I have increased the pressure. I've squished them all together. And in order to resist the effects of change, or to reduce the effects of the change that I've made, it is going to try and make fewer molecules. So it needs to have less things present in that jar in order to maintain equilibrium. So again, we've got 4 molecules of gas on the left-hand side and 2 molecules of gas on the right-hand side. So the system will shift to the right. It will have the forward reaction in order to turn these 4 moles of gas into 2 moles of gas and effectively halve the number of molecules that are present in that container. So how will the system reduce the change? It will move to the right / favour forward reaction / favour products. It doesn't matter how you write this, as long as it's kind of one of these 3. So move to the right, forward reaction is favoured, products are favoured. They all mean the same thing. Pick your favourite. In order to make fewer moles of gas. And reduce the pressure. Hopefully that makes a bit of sense. So it's kind of like a spatial concentration. Are there too many things all crushed together? If so, I'm going to try and make less things so we've got more space. And this only works with moles of gas. So if I had something aqueous in here, it would not be considered as part of my consideration here for affecting pressure. So the aqueous wouldn't affect this at all. So just gaseous moles. So the last one here is temperature. So temperature is the trickier one, and it also helps, it doesn't help, but it's difficult because you also have to remember what these signs mean from last year. So remember that a positive enthalpy means that it is endothermic. So that means that it is absorbing heat. So it will go colder. Make go cold. if there is a negative enthalpy, it is exothermic because the system is releasing energy, so the energy of the system decreases. Make, go, hot. So these temperature things are important. So the endothermic reaction will make it go cold, and the exothermic reaction will make it go hot. So exoplosion, giving out heat. Now, here we've got our reaction from before, and we can see here, that our delta H is equal to positive 92.4 kilojoules per mole, which means that it is absorbing heat in the forward direction. So the delta H that you're given is always for the forward reaction. And they always come in pairs, which means the backwards reaction is the opposite. So that means in this case, my forward reaction forming ammonia is positive, so it's endothermic, but my backwards reaction, where the ammonia turns back into nitrogen and hydrogen, is exothermic. It must be exothermic because it is the opposite. So what the system will do in order to reduce the effects of change, so if I increase the temperature, so I start to heat it up, the system will move in the direction that will reduce that temperature. So it will move in the endothermic direction to make the temperature lower because the system will absorb that added heat. So it will move to the right / favor products / favor forward reaction, because the forward reaction is endothermic. It will absorb that added heat and lower the temperature back down. If instead I lowered the temperature, so I stuck it in an ice bath or something like that, so lower temperature, the system would attempt to increase the temperature back up again by moving in the direction that releases heat. So it's going to want to heat up its surroundings again. So the system will reduce the change by moving to the left or favoring reactants or favoring backwards reaction, because the exothermic reaction, the exothermic direction moving backwards, will release heat and therefore increase the temperature back up again after I have put it in something cold. So the main thing to think about with these equilibrium reactions, and particularly because we're only really going to be thinking mostly about concentration, is that whatever you do to the system will try to fix. So if you add something to the system will try to react it away. If you take something out of the system, it will attempt to make it again. And whichever direction of your equilibrium reaction will achieve that aim is the one that it will favor. Hopefully that very quick crash course was sort of helpful. If it wasn't, please let me know. If it was, please let me know. Validate me. Make me feel better, please. I hope you're all well. If you're not, please tell me so I can help you. I will see you later. Click the notification bell. I don't know how to do this. Okay, goodbye.